question about part 2. That's why. The second question that you can't have x equal to 0 for y equal to 0.
Oh,
That's where I
yeah,
was,
yeah.
that's what I did wrong.
You said,
Yeah, there.
word. Glad we're on the
Yeah.
same page. So you do number 2 yet?
Yeah.
How did you start?
Well, it doesn't have an identity.
Oh, sorry. I didn't even get what it was asking. That's it?
For each.
For the power?
Like the second question I meant.
Oh, no, like the second.
The second question, I didn't look at it.
Okay.
The rest of it worked out just fine.
Okay.
Something power sense.
All right. So we are talking about confidence intervals, and we want to look at different ways to make confidence intervals. And so today we look at bootstrap percentiles. So a way to do simulation to get at the confidence interval and try to understand a little bit more the basis for why this is working, kind of an answer in a general sense, right? So, and one thing we'll talk about, and the book uses, is this capital F, this cumulative distribution function, and understand how that plays into this and what that means. We won't do much analytic work with cumulative distribution functions. That's more something of probability theory to look at those and differentiate those and so on. But it's useful for describing a distribution, a population structure. And so we'll understand that. So the scenario we're in, right, is we have a sample of values, x1, x2, up to xn. And we have an interest in a parameter that describes something in our distribution, such as the population average. Right? And we're going to have a statistic, which could also be viewed as an estimator. A way of going about estimating things. And so we can take the sample average, x bar. This mu is a population average, is what we mean by that symbol. Right. And this x bar is the sample average as a standard way of estimating that. So x bar is just we add up all the values and divide by the sample size, and we get a sample value. But we know that that's probably not exactly mu. We already know the level of accuracy. So the bootstrap percentile method is we generate different bootstrap samples, and we look at the simple 95% of those. So confidence interval for mu. And we'll do 95%. That's a standard thing. You could modify that. So we're going to generate bootstrap samples, and we'll say exactly how we're going to do that shortly. And each bootstrap sample is going to give us a different average. And we might have, 1,000. The book suggests 10,000 bootstrap samples. So some discussion about that, about how many do you want to have, right? And then we're going to look at the central 95% central values of our bootstrap sample averages. Right? So we need some way to pick these bootstrap samples that's consistent with our data and models and hypotheses and things like that. And so one way of doing this is just resampling from the data we have. So a bootstrap sample of size little n. They're n data points, so our bootstrap samples will also have n data points. Is randomly pick n values from our original data x1, x2, xn. Put it that goes in a set if you like. With replacement. And so those new values are could be called x1 star, x2 star, etc., xn star. And we get our new values, and we use those to calculate one average. 1 over n, the sum of the xi stars from our new samples. And so that's one bootstrap sample, right? That whole process, right? And one value of statistics from that sample. Right? By picking with replacement, right? We start out with all n, pick one, and we have all of them again, so we can pick the same value multiple times, many times in fact, and we can leave out some values. So each bootstrap sample looks a lot like the original, but it can potentially be a little bit different. The idea is this was to show you what other samples might have looked like, and so this will show you, if you do this enough times, what the distribution of these x bars could have looked like in different samples, and if that mimics the population sampling, that would give us some idea of how wide our intervals should be. And the bootstrap percentile thing is kind of an easier way of doing that. Right? That's the procedure. Now I'm going to talk about what motivates this. Right? How do we get around doing that? Right? What part of this do I want to talk about? Right? So let's kind of put it in the overall. Why does this work? Well, we have our sample, and we have our statistic. The book calls it T, which is h of x, or if we want to write out all the different, something like that to show that we actually have n observations. Now, if we had many samples, we would see how variability from sample to sample would be, right?
What does the H stand for?
That's just the kind of the book's notation for some statistic or estimator. I don't know a word particularly that would be in that age, but they just use it as some function. So, the example we use on the other page is x bar, but it could be medians or trimmed means or standard deviations or 1 over that. So just some useful function.
A summarizing function of the
Some
data.
type of summarizing function of the data. Yeah.
I don't know if it had any significance. The book didn't say anything. So.
Yeah, I don't know that would be used so typically.
Yeah.
You might have just put T of X to say it's some statistic or testing. Hypothesis testing. T might be a hypothesis testing, but it's just some summary that's in there. So if we had many independent random samples from the population, so we had T1, T2, 1,000 random samples, then we could have 1,000 values of the statistic. Right? We then could assess, the variability of our estimate. And we could put some type of interval around that. We could look at the percentiles, how wide intervals typically are, standard deviations of these. Right? But we only get one sample. So instead, if we could create an artificial population or an approximation to a population, and we sample from that, it could kind of do the same process. So instead of having independent random samples, we want to create, you might think of it an artificial population. or you might think about it as an approximation to the population. Right. And sample from that. Sample repeatedly from that. And to the degree the artificial population or the approximation is similar to the original population, then sampling from it is like sampling from the original one, and it all should work out pretty well. So the interval we create through this artificial, sampling from this population would be relevant to our overall population, right? And so the book talks about that as a plug-in estimate, right? And so scientific terminology of plug-in, right? So you have something you want to use, and there's some unknown value or some unknown characteristic, so you just take your sample and get some estimate and plug in some number. Maybe you know something externally, like have a hypothesis about certain values. Maybe that would tell you some numbers, and so in a way that might be a plug-in or estimate for something. Maybe a process is engineered to be a certain way, and for the time being, you're using the kind of specified tolerances or theoretical assumptions about what those should be. Right? In our cases, often we have data, so we're going to estimate those things. Right? So this artificial thing here, the book talks about plug-in. We're going to plug in some reasonable value or estimate. The first time I heard plug-in, I thought, well, that doesn't sound very precise or fancy, but that's kind of what we do. So, and so what are we doing? This is done all the time. Right? Often we're interested in a parameter, like mu or sigma or a proportion, something like that. And we often, have an estimate. And in a way, you can view that as plugging in some estimate or taking our data and getting some value. So like the sample average for that, or sample standard deviation for that, or a sample proportion for these. These are all sample values, which these either come, they can be thought of coming from a population, or they also tell us things about probability models. The mean and variance of a normal distribution tell us all we need to know about the probabilities from a normal distribution, right? Binomial sampling experiment, the proportion is the key thing, and once we know that, that tells us what the results would be if we did it again and again and again, right? Sometimes there are alternatives. To these things. So instead of taking just a sample average, well, the sample average is very sensitive to extremes, right? If you get a very large value, a very small value, instead of plugging in X bar for mu, you might think, well, in this case with a lot of outliers and things, I might drop the largest observation and the smallest observation, kind of do a trimmed mean. That's less susceptible to extremes, like one extreme value, particularly in a small sample, right? So you might do 1 over n minus 2, and then a sum of the x of i's for I going from 2 up to n minus 1. Now this little thing is is kind of standard notation for the ith largest of the x1s up to xn. So if you put all the values in ascending order and dropped out the smallest and dropped out the largest, this would be one way of kind of putting that in a formula, right? So there's alternatives, right? Eventually we're going to study how would you evaluate different plug-in estimates or different estimators of parameters and things. Each time you plug something in, you get a little different performance, right? Maybe you get unbiased, there's a variance. Some estimators are biased, but they have smaller variance, so there's something called mean square error that kind of does both of those things together. And in the bootstrap you can think about the bootstrap as a plug-in estimate for the entire population. Right? In particular, this F, right, the cumulative distribution function, in a way describes probability models and can describe the population. And what we're dealing with over here is an estimate of that. Estimated CDF. So the bootstrap helps us plug in or estimate that entire population there. Right? So let's talk a little bit about these CDFs. If you take in probability theory, you've seen these a number of times, but it's something that even if you haven't seen that, we can talk about it and get a sense of what it is. Again, we're not going to do a lot of technical calculus with it, to operate with it, but it's just a fact of life of reading the book and of dealing with these things. Right? But any questions about this? So we'd like to have the population, but we don't. We're going to use our data to get an estimate of that. Instead of sampling from the original population, we're going to sample from that, and that's what the bootstrap does. So what are these CDFs? Well, say you have a normal distribution, right, by this, and here's a little value x, and here's mu in the middle. This is also the median value because it's symmetric, 50% on either side. When a plot like this is a little f, right, it is a probability density function. Right, or PDF. And so it kind of shows where the likely values are. Right? It's more likely to have values that are close here in the middle. And as you go further out, according to a certain decay, it becomes less and less likely. Right? The height here are not exactly probabilities, but the area in different intervals gives that. And under this, the area under the curve, total area, under curve is 1. Yeah. Right? And so any fraction under an interval gives that probability. Now the cumulative distribution function, f of x, right, is a probability that x is less than or equal to something. Right? So essentially, it's you choose a value of x here, right, and then you look at the probability underneath that. So it's really an integral. And this is the letter x. Right? These cumulative distribution functions are between 0 and 1. Right? If x is very low, you have no chance of being terribly small. But as you get further and further out, you've seen all the likely values you're going to see. And so if you graph this function, the f of x goes between 0 and a maximum value of 1. In this case, it's that symmetric up there like the normal. Mu is right in the middle. So if I map this down here, mu, it occurs at 50% probability. Right? And as you come along here and kind of gradually add up area, it starts out pretty slow. Right? There's not much probability at first. But then once you come along to the middle, there's increasing probability. So the cumulative area as you move this way is increasing pretty fast. Now it's at 50%, and it's still going up pretty fast with slowing down. But out here, it's still going up, but slowly. So the cumulative plot, based on that, it's kind of coming along here slowly, and then it kind of sloops up, comes up here, then asymptotes at 1. So you have a particular value, I'll just call it a value S here, I think the book uses. The probability that a random variable x is less than or equal to s is this cumulative evaluated here. So S I put out a little bit too far. Let me put it over here so that it's not 1. So the probability over here, you're going to map over to here, and that's going to be the probability. Let's say that's 0.9 over here. If that's where it maps to, would be about 90%. That you're less than or equal. So knowing these cumulative, knowing the form of this function or being able to evaluate it, describes the population. Right? Describes how the range of things in the population that are likely to happen. Right? And as you get different populations, this curve is going to change differently, right? So we'll just illustrate a couple quick things. So if you had a curve that was pretty skewed like this, right? So at 0, if it's kind of a positive variable like that, you know, in this one, the mean is somewhere up here, and the median is a little bit lower, right? Because this large tail means that the average is pulled up higher. So it's cumulative distribution function. So this would be the density, the lowercase one. And if we integrate going across this way, well, it's here's 0 and 1. Here's the cumulative. It starts out. There's no probability at all before 0, right? So it's going to be there, and then this thing is going to shoot up pretty fast, right? Because there's a lot of probability here. Right? At the median, though, if that's where it would be, right, it has to be 50%. So maybe the median's back a little bit more. Let me move it back so my graph is more to my liking. So here's the median. That's at the 50% point. So this thing is going up pretty fast and then kind of leveling out. Right? It takes a long time before it actually gets to 1. That's not a great picture. Or maybe it kind of goes up a little bit more. Like we're supposed to go through the median is supposed to go through. But anyway, it goes up pretty fast. It's 0, then it goes up quickly, and then it levels off really fast. And you get different pictures of things, right, with a different pattern. If you had a distribution where the density was something kind of like this, this could be kind of a mixture. Like maybe you have one group over here and another group over here, and you put them together, and you can get a density that looks like that. So the probability is not one curve, right? A cumulative distribution function for that one. It kind of looks like a normal with a little flat spot in the middle, and then kind of goes. So it kind of tracks that. So that's kind of the population. Right? And if you wanted to sample from the population, we think about sampling from the population, going out and get somebody and measure them. One way of thinking about that in terms of this kind of formulation was, well, use this cumulative distribution function to pick a value from the distribution, right? So if we wanted to sample from this one, these things are between 0 and 1. They're probabilities. And so one thing we can do is choose a random probability, a random number between 0 and 1 uniformly, map it over to this, and then map it down. And if the median is here, that's 50%. It's not a very good picture to use. Let's just put one line in here going through the median, right? 50% of the time we're going to be below the median, and 50% of the time we're going to be above, because 50% of our random numbers are going to be below and up here. And we just take some random number u for like a random uniform, and map it over to this thing, and then map it down. Right? So we'd end up there and get a value of x. So a way of generating a random sample is to let u be distributed as a uniform random variable between 0 and 1. So we get a random value of u. It's going to be somewhere between 0 and 1, a certain percentile, uniformly between there, so they're all, any values are equally likely. And we let x equals the inverse of that x function at u. Right? So if we had a bunch of u1, u2, u sub n independent random variables from a uniform, and then we let x sub I equals the inverse of that function, right? We're going to end up with x1, x2, xn that are a sample from our population, from this probability model which describes our population. So the cumulative distribution function kind of do that, right? And you do this with discrete things too. So they don't have probabilities at every point. Right. Let's do one discrete picture. So let's say x is discrete, meaning that x has values at certain points. Let's put probability here. Let's put, maybe this is x, and here's the probability that x equals some value. Right? You either get this, 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 or this, or this, or this. The cumulative distribution function is meaningful for this one too, right? But it's discrete. So we go along here at 0, and at this point we jump up a certain amount. Right? And then we go along, and there's no change because there's no probability between, and at this point we jump up here. Right? And then we go along, and this one, there's a bigger jump, and then a smaller jump, and then a small jump, and we're up to 1. Right? So we have a certain probability jumps as we kind of go along that, because it's more of a step function. Right? And so if we wanted to generate from this, we can generate a random uniform number. Say we generated a uniform number here. Well, we can translate that into a value of x. Right? We can map this over here until it would kind of hit something like this. Right? And then what we're going to do is take this value up here as the random value. Right? So there's a certain probability that it's this first value, this probability that it's the second value, this probability that it's the third value, a certain probability that it's the fourth, and a certain probability of fifth, where these little posts here kind of correspond to that. Right? So you would map this one back and say that's my value of x. Right? And so this f, this cumulative, kind of represents a population. Sampling in it, you could kind of think about it as taking this. And so what the bootstrap is doing is approximating f, right, in a way, right? So, let me put that. Right. The pins communicated, it was still. So the bootstrap plug-in approximation to this cumulative distribution function. So we have x1, x2, right, up to xn as values. Right? And so we can do this empirical cumulative distribution function, f hat. The book has some graphs of empirical CDF, step functions, going up, right? And that's why I think it has those as one of its graphing options. So here's our values of x, and say we have x1, x2. I'll put these in order, even though they wouldn't necessarily have to be in order. Maybe x3 and x4 is here, and x5, and here's an x6, right? So let's say we have six points. Right, so we're going to take 1 over n, height. We're going to jump up 1 over n at each value of x of I that we have. We're going to get a little step function that way. Right, so it has to go up to 1, and so we're going to have a little jump up here, and we're going to do another little jump here, and then we're going to do another jump here, and another little jump here. I'm going to connect these a little bit here. Right, and then the next one jumps up a little bit, and this next one jumps up. These are supposed to be equal jumps, and then I make that one. So that it's so there's a kind of this step going there, right? And that's kind of an approximation to the cumulative. So we kind of plug that in as an approximation to the population, our estimate of this model, this cumulative probabilities. Right? And then we sample from it. Right? How do we sample from it? Well, we would pick a point, right? We'd pick some value of u, and map it over here, and it would hit this one. And so if it hit here first, say that's our first one, we would take x of 4. So our x1 star, our first one is going to be copied over that value of x of 4. And then if we sample our second one here, kind of mapped into this place, right, x2 star, our next one would be x of 1. And we're going to do that 6 times in this case because sample size is 6. But we're going to take independent samples from this thing. And it's equivalent to, because of the equal probabilities, of just randomly picking from our x1, x2 to x6 with replacement 6 times. Randomly picking. So the thing that, randomly sampling from our original data with replacement is implementing, right, sampling from this empirical distribution function. So we've approximated it, and if it should do, you could talk about this if you have a large enough sample, so it's pretty representative of the population, right? Then sampling from that can do quite well in approximating the population, right? And so sampling for this to be very simple. Maybe it's really a continuous distribution, right? So if it's really a continuous distribution and it looks something more like this, so we don't have it exactly, but it might capture most of the essential variation and be useful for our intervals, right? So if we take one sample, right, we get 1 x bar star. We do that 1,000 times, 1,000 x bars, and we can take the central ones, call that an interval. Right? It should be, our actual sample should be pretty much right in the middle of that. It might be off from the center a little bit, but it's going to be pretty much in the middle, right? Because the extremes of this resampling, you get the smallest observation 6 times. Or you can get the biggest observation out of the original 6 times. But you're probably not going to do it that much. You're going to get some type of mix. With only 6, you might actually get, if you do it enough, eventually we'll get the extremes. But ours is going to be pretty much in the middle because it has the smallest and the biggest of our 6. It's kind of a nice mix in there, right? So that is something about this plugin, right? What's going on with that and this bootstrap and why it seems to work. Now with the plugin, there's usually multiple ways you can do one thing. And this empirical CDF approach is one way to approximate the distributions, but there's other fancy things, other ways to go about this, right? So instead of doing the empirical CDF, so one way, blue, right? Empirical CDF, right? Right? So this is kind of the bootstrap resample n times with replacement from our original data. Another way that you might see now and then is use a model. Right? So for instance, an exponential random variable has one parameter. So instead of resampling from our data, one way about approximating that population and getting a cumulative distribution function is to plug in lambda hat, and the usual thing is 1 over x bar, in there, and then our bootstrap samples from, we could sample from an exponential random variable with parameter lambda hat plugged in to our sample value. So this exponential, right, is a probability model. This is the cumulative, this is the density function. Right? It's positive and decaying so that the probability that you're near 0 is pretty high. But this tail can go out for a long time, so you can So kind of used for waiting times or streams like that. So instead of sampling from our x1, x2 up to xn, once you plug in a parameter value, analytically we can sample from this thing. There's a random exponential in there. So that would also create an approximation to, right? This is our source of f hat. If we use that model, right? And sometimes that gets done in things. Right now we're just going to use the empirical one, right? But in some cases, I have a kind of a small sample. Maybe and I'm particularly interested in that model. Maybe this is a little bit more smooth, right? In the sense that I don't just have those 6 points. I can get any points. So maybe that would be, right? So there's different plugins that have different properties, and ultimately we'll try to figure out how do you think about these things? Which one's a good one to do? Right? What would you want to check to prefer one over the other? There's other things in where you take each of those xn's and you put a little caliper or a little bin over there. You kind of take a little normal probability around all those, and you add up all those little curves. It's kind of kernel density estimates. That there's different ways of estimating curves, and so it can get kind of sophisticated. You can estimate it with penalties, so they're smooth, and other things. But there's a kind of a third more, an empirical way, some standard model, or then these more machine learning, slightly more complex things. But they're all doing plug-in estimates for that, right? So let's use it in a couple examples, right, and see what happens. So the next homework will be posted pretty soon. If not tonight, then early tomorrow. And would have you do a little sampling to show how sampling from distributions works, and then a couple bootstrap examples. So, I'll take that later. So on the handout, does everybody have a copy? Everybody has a copy. There's 2 data sets that are used in this chapter, one on arsenic in wells in Bangladesh, and then one on births in North Carolina. So I read those data in. The arsenic data set actually has 3 variables. They measure arsenic, cobalt, and chlorine in the water samples. In a real biological example, you maybe measure certainly pH and maybe a dozen other things of concern. It's good to look at the top of it. It's good to look at the tail, the last observations. One thing that just happens to pop out in the last observation is there's an NA, so some of the measurements are missing, right? So either they didn't have enough water to test it, or they sent it out to a lab and it was a faulty reading, or something like that. It happens. Right? To make it easier to use, I'm just going to attach the arsenic. So under these, in the environment here is this arsenic, and it has these 3. So I can just type capital arsenic, or capital chlorine, or capital cobalt, and I get those variables. I don't need to do the $ sign to refer to them. The arsenic one, here is the plot. No, let's try that again. Arsenic, very skewed. Some wells have a big concentration. Right? Very skewed. One thing that's useful for comparing distributions is this cute norm plot. So what this does is take the theoretical spaces of the normal and compare them to the spacing of the actual values. Right? So the sample values are here. We know that there's a bunch of small ones and then a few that are really extreme. Right? And so if our data were more of a normal plot, right, this would be more straight. Kind of the relative spacings of a theoretical normal and an actual data would be kind of similar in scale. Right? And so this would be straight. So this is just another one that shows that this is very non-normal. But we know that from the plot. How about chlorine? Yep, it's skew. Not straight at all. Cobalt, still skew. So these are all 3 skew variables. Now we know there's some are missing. So arsenic, how big is this, right? Is a matrix, right? So it's 271 rows actually. but then 3 variables on top of there. Right? The top of it, right, is this. Right? So is.NA, right, is a function, say you put the number 5 in there, not missing. NA means not available or missing. So if it's a number, it's not missing. But if it's that is.NA, if it's missing NA, right, it's true. Right? Some computer programs, or some people in their data sets will put like a -1 or a 99 or something like that. Or maybe they do the responses 1 through 4 for categories, and number 5 is NA. So you always got to know how people are coding things. R by default calls NA that. If I do it to the entire matrix, right, it will do NA for all the rows and all the columns at once. And then I want to count how many by column are missing. So this apply thing will apply the sum command to the second dimension. So this is a quick way of doing that. And what it does is arsenic's not missing, chlorine's missing 2 times, and cobalt's missing once. It's good to look at your data, whatever analysis you're doing. Right? The average arsenic was 129. Now let's do a confidence interval for arsenic. Let's do 1,000 simulations. I'm going to save the bootstrap averages in that boot A, bootstrap averages for arsenic. And there were 271, so I'm going to sample those with replacement. There's the sample command, I'm going to hit the average. So that implements it. Do it 1,000 times. So that's all set up there. Click, click. Here's the 1,000 averages. The original data for arsenic, I don't know if I would have to go back a little bit. So the histogram for arsenic, for big A arsenic, was like that, right? 0 up to past 2,000. Now the average of 271 is in a much more narrow range, right? And on our average we had before of 125, it's pretty much right in there. Right? So our interval, if we take the 2.5% percentage point of this distribution and the 97.5% percentage of that, that gives our interval. If we illustrate that, purple this time, right? So this is our 95% interval from that simulation. We had our original data. We sampled from it. That's like approximating the cumulative distribution function of the population model empirically. We sample from that as if we'd sampled a whole bunch of times, 1,000 times, and these would be what we would get. And it's kind of centered around our data because it is resampling our data. This histogram of those things, it looks much more normal, right? Much more straight line. This, right? This is the histogram of the bootstrap averages, because averages are much more normal than individual values, right? And so you get that looks much more. What about chlorine? Right? The mean of chlorine comes back as NA. There's a missing value. R by default doesn't do anything. It doesn't make it 0. It doesn't delete it. It just leaves it at NA, and so the sum it can't be computed, right? Which is kind of good. Some software programs will put a 0 in there, or just drop it out, or not tell you what they're doing. You're supposed to pay attention and know. But you can tell it to remove that, and it gives an average of chlorine. Here's the histogram of the chlorine values. It's hard to even see where that would be. The average comes out being 78. A lot of those are really small. We bootstrap chlorine. I've changed it to be this big. I've changed it to put a little C here to keep track of chlorine. This is chlorine, right? And instead of the NA, I've had to make sure that the NA dot remove equals true. It's just a coding thing if we're dealing with missing data, right? It has to be in there. So if we do that, there's the histogram of the bootstrap things. There's the interval, and it would be 55 up to 104. And again, the sampling distribution of the average based on 271 looks a lot more normal than the original. Right? Now you might think of one other way of doing this. So I took 271, right? I originally had 271 samples. And sometimes they're missing, and sometimes they're not, right? And I had one missing, or maybe two missing for chlorine in the original sample, right? Now my bootstrap samples, because I'm sampling from all 271, I might get more. I might get 4, 5, 6 missing, right? I'm not only going to get 2 missing. A different way to do it, right, would be to take out those 2 and say I have 269 measurements and sample from those 269 times. Is there any difference between doing those 2 things? Admittedly, it might not be too big because it's 2 out of 279. It's not 50% of them or something, but how will that affect things? One time you always get a sample of 271, right? Some are missing. Another time you get 269, none are missing.
So it would probably be higher on average?
It could be,
Or like lower, higher or lower on it?
yeah, so I think the variability, right, really could be affected a little bit. Right?
Because it's only 2, not that much.
Yeah, right, but it's just a little bit subtle difference, right? You could handle it different ways, and in other applications, missingness is kind of suspect, right? This one might just be a lab error, we don't know why. But other times, the missingness might be more informative, right? You're asking people how much they smoke, and some people said, no, just refuse to answer. Well, is that really a 0, or is it an average value, or what is it? So it might mean a little bit more. Right? But it also affects the variability, right? So where is that affecting? Right, that plug-in estimate of F, right? Our empirical CDF, how do you want to do it exactly? It'd be subtle. I don't think it'd make much difference in this case, right, to do it. But you could take out the missing values and then simulate it. This simulated it, and it could have that, you could end up with more than just 2 missing. Or you could end up with none missing. Or you could resample and miss those 2 completely. That's very plausible. So your samples have different sample sizes, but that might contribute to a reasonable assessment of variability. Maybe that's good. But anyway, that's just a little bit about missing data. It will affect your analyses. If you continue using R or any statistical package, it has to do with missing data. So. Another data set they have is births. And these are births in North Carolina. So they have mother's age, they use tobacco, alcohol, gender of the child, right? Weight in grams, a kilogram, 1,000 grams, about 2.5 pounds, so 2.2 pounds, right? And so 4,000 would be almost 9 pounds. Gestation would be birth at gestation, 37 weeks is term. Earlier than that would be premature birth to some degree. Most births don't go much past. Are these all term births? Let's see. Table, births, $sign gestation, station. Yeah, these are all term births, right? But not many go much past. If the baby's not being born, you can induce labor or something like that, or a cesarean section, right? So usually it doesn't go much past. It's not necessarily so good for the mother or the baby to be in too long. Right? And we could be interested in something like the proportion of mothers who use tobacco. So is tobacco one? If you tabulate it, 100 yes, 898 no. Are there any missing? Oh, check for missing. I do that this next part, right? Is.NA applied to this, we just create a vector of trues and falses. If you add up true and false, it counts true as 1 and 0. So this thing is a value of 0. Is.NA. Just take a look what that does. Births, tobacco. If you look at, say, the first 5 values. False, false, false. They're not there. Are there any missing values in this entire data set? Is vitamin A, Earth's? Nope, nothing's missing, so it's complete data for this one. You can force tables to have a count of missing. If there is missing data, tables usually don't show you. It's just that's how they've given it as a default. But there's none here, so there's nothing to worry about. The proportion, 1111 out of the 1009, is about 11% of mothers using tobacco. I don't know, is this when they're pregnant, before they're pregnant, or when they're during pregnancy, or just before birth or something, but some are using it. And so we want a confidence interval for that proportion. So we can use a bootstrap, we can resample from the data. The data are going to be these yes or no values. There's 1009, so we're going to resample 1009 of those with replacement. We're going to get a mix of yeses and nos. And the number that equals yes is, we're going to take, by taking the mean, right, it takes the number of yeses divided by the sample size. So p hat, the sample proportion, is really an average. Right? It's an average of ones and zeros. So anyway, that's our bootstrap. That's the histogram of the bootstrap. Means, my proportions, my 0.11. 0.11 was our sample value. There's where we'll get our interval, and there's the numerical values in there. This sampling distribution also looks pretty, extremely quite normal, right? So in your last homework, you did a confident, 4 probabilities for a binomial, right? And so it's very similar to this, right? So what's the standard deviation of these bootstrap proportions? About 0.095. So, what was that? 0.11. Well, that's, you can either take this whole number or just take 0.11. Right? You take square root of p times 1 minus p over n. It's just about the same. It's, if I did 1,000, if I did 10,000 or 100,000 bootstraps, I bet I'd come really close to that theoretical one. Right? So it kind of reproduces what you would get from a normal confidence interval. The p hat minus 1.96 times the standard error from a normal, from a binomial formula. But this one does it for that too. And so again, what we're doing, so the kind of big theme is our goal as an inference for a parameter, say theta generically. We have an estimator. T is some function of our data that estimates theta. You might call it theta hat to make it specific to that in your symbols or what you're thinking about. Right? And then we want to know what is the sampling distribution of T, our theta hat. And so we're going to approximate the CDF, right? And then we're going to sample from this and get a bunch of different values of the statistic from that sampling distribution. Right? And turn that into a confidence interval or percentile interval. And this process of doing this, right, is this bootstrap resampling with replacement essentially implements that approximation for us. So we can get intervals. And it's pretty flexible, as we saw some examples the other day. On Friday, we will keep exploring this a little bit more. In some cases with Bootstrap, it kind of has a little problem. Right? Medians or small sample sizes, some things can be a little bit funny, but generally it's pretty flexible. Any questions? Okay, so we'll stop there. If you have the new homework, give us a trial started here for those. Good one. Okay. Both of them? Yep. This is the portion one?
Yeah, it's the last one.
So, yep, so this is going to be the thing that happens there with the binomial.
So the extra. Yeah, because technically here's what exactly the equation was.
Yep.
Kept switching the variables.
Yeah. So this is a proportion. So I'm going to write something on here, and you can take it and
Yeah.
write it. So we want that we were between 220 and 230
Yeah.
in there. So this x, this proportion, so we can change this, divide everything by 800, and it's a sample proportion.
Alright, so that's similar to what I did there.
Yep. Yep.
And then that's your proportion that you use that as.
Yeah, and so what you use is this p hat is going to be approximately normal
Right.
in the central limit theorem, and the census says it's 2.86. Right. That's going to be our value of p.
Okay.
And then for you need a standard error. There's a formula p1 minus p over n.
Oh, okay, that's what I was thinking for.
Yeah.
Because I couldn't seem to find, because that would go in there, and then how many samples would there be?
It gets incorporated in this n. So, right, so this is the general formula.
We still never got n, did we?
N is going to be 800. There's 800 people in the sample.
Oh,
So,
okay, yep, I see what it was.
but
So that's-
once you calculate this, you don't need to have another square root of n, right? This thing is this entire thing sigma over square root of n.
Okay.
Right? So, yeah, you would.
So you could plug that in.
Yep. You're going to get a z in the middle and calculate two things.
Alright.
Yep.
Can I just redo that now or turn this in as it is?
You can redo it, and I might have to go, so if you're working on it later and want to slip it under my office door, would be fine.
Alright, yeah.
But, yeah.
Shouldn't take long. Alright, yeah, sorry about that. I was trying to figure it out.
No, that's, you're not the only one that's asked that question, so. Because that's the big question, is where's that sigma, right?
Yeah.
On those, yeah.
So so sigma equals p, 1 minus p. Like,
Yes.
yeah, okay. Divided by m.